We'll go ahead and get started in the afternoon session. So we have a return performance by Ian Corner from the from the Australian, I guess you'd call it their centralized research agency, CSIRO. He can tell you what the acronym means. But basically, I met Ian in my a couple years ago. Was visiting Australia, talking to customers, and was really quite amazed at what they were doing there and some of the models and techniques that they had been developing to help understand how lots of data moves through an organization and how to make that process a lot more, well, bottom line, a lot better in many ways. So Ian's going to be giving a talk, and then we'll follow up with a panel with folks who are kind of working in the same area and working with him towards this goal of supporting data-intensive workflows. Ian?
Thanks very much, Matthew. So yeah, CSIRO, which you can pronounce CSIRO, CSIRO, or Commonwealth Scientific and Industrial Research Organisation. So it's a mouthful. Today I'm going to do a high-level overview of our approach to data-intensive workflows. A bit on my background, I've worked in the IT industry for around 30 years. It was predominantly in mission-critical, high-availability environments, in secure sort of institutions that you can't talk about. But for the last 5 years, I've been working with CSIRO with a specific focus on comprehensive management of data assets. And this notebook is very slow. So a little bit on CSIRO. We've got around 5,300 talented people working out of 50 plus centres around the globe. We've got $1 billion budget, and we generate about $500 million from external revenue. If you look at us from a research perspective, we're in the top 1% of 15 out of the 22 fields of research that we participate in, and the top 0.1% in 4 of those research fields. Our people work closely with communities seeking to leave a lasting legacy, and our focus is practical, so we're always looking for ways to help business and industry. Our mission is to create value for customers through innovation that delivers positive impact for Australia and the globe. For anyone that's been following the Australian political scene recently, you'll see there's been a renewed focus on investing in innovation. This is something that internally we're all quite happy about, and it's seen the establishment of a new part of CSIRO, which we refer to as Data 6.1. CSIRO is the largest patent holder in Australia, and that wealth of intellectual property has been spun off into more than 150 startup companies. And I think the success rate of those companies is pretty good. It's in excess of 70% are still in existence. About 1/3 of all our intellectual property is licensed, and I guess the quality of our research underpins our ability to innovate. Sorry, computer's a bit slow. So, CSIRO's history goes back 90 years. We hold an insect collection with 12 million physical specimens, 5,000 species of fish, microalgae, and we have 1 million herbarium, some dating back to the original exploration of Australia. And this stuff is actually gazetted in law. It's not something that we just keep as a convenience. We're mandated by the Australian government to preserve this. The key here is that yesterday's collections were physical, captured and preserved. And while we are rapidly digitising these specimens, there's a bit of a backlog there. You know, if you think about digitising 12 million insects at 30 gigabytes an image, then there's a lot to do. Just get your camera out and spend the weekend and see how many things you can photograph. And that collection, I think, is growing at roughly 100,000 insects a year, so it's going to take a bit of work to catch up. Importantly, we need these digital specimens to be discoverable using today's technology and consumable for all the interested parties. So one of the key funders of the Australian National Insect Collection is actually the US National Science Foundation, and so having this stuff online and readily available is a key part of the strategy with respect to this. And while yesterday's collections were physical, today's collections are often digitised in the field and transferred by remote sensor networks or physical media directly into our long-term storage facilities. And it's programs like the RV Investigator that are heading up this type of thing. I think organisationally there's about 140 sensor projects going on. The RV one is probably more of most high profile. The vessel is bristling with sensors, and on the last voyage they added an additional 30. So the IT guys were pretty busy then. 30 new sensors. I asked them about it. I said, "You seen these things before?" No idea what they are. So, and just stepping back a little, sensors are proliferating at an unforeseen rate. They're easier to deploy, lower cost and higher resolution. This is every researcher and scientist's dream. And vendors have come up with a new name for this too. They call it the Internet of Things, which is great. We've been doing it for a while. It's good to have a name for it. The question you've got to ask, though, is what good is all this data if it's unable to be processed? And so we're going to go back a little way to where we started. About 5 years ago, CSIRO had reached a point where our breadth and our ambition totally outstripped our funds. We couldn't do what we were trying to do based on a traditional approach, and so we were forced to rethink things. We had to ask, what good is our data if it's unable to be found, if it cannot speak, if it only ever repeats the same story twice? If it only ever repeats the same story, or worse, if it can't repeat the same story twice, or if it speaks so slowly that the message is lost. With this in mind, and with 4,000 or so research projects on the book, we started down the path of establishing fit-for-purpose infrastructure and layers of automation that supported our anticipated data storage requirements. And I guess it's more than just about the infrastructure. Where we were was on the path to the monolithic storage of data. Each data centre presented monolithic file systems. Any major change or downtime required organisational-wide consent. It was a general solution, trying to be everything to everyone, but it was optimal for no one. And on any given day, a researcher could break the infrastructure. Why? Well, not because there was anything fundamentally wrong with the technology, but simply research activities always far exceed the hardware level capability or optimisations. Furthermore, the data stored in these global file systems lacked context and were subject to traditional backups, which we found just wouldn't scale. Backups as an afterthought were becoming an increasing liability. We split the monolithic file systems into named and discoverable datasets. By dividing into datasets, we took the first step in making the data discoverable. Then, regardless of the internal structure, content, number of objects or size, we established a boundary where network protocols of best fit were presented and a security perimeter established and maintained. And this started to unpick a whole lot of legacy issues inherited from the monolithic approach. For example, a downtime now for a data set required only talking to a few of the data set owners and contributors. It didn't require organisational-wide exercise involving 5,000 people. Eventually my finger will get ahead of my mouth to make up for the lag of the computer. Suddenly, so if you look at the dataset approach, it also delineated the responsibility between infrastructure owners and dataset managers. Suddenly who is responsible for what became clear. And that's not to say that infrastructure can be ignored within the dataset, nor data management outside, just that there was a line that helped avoid overlaps or areas where responsibilities were otherwise missed. And furthermore, we've found that this facilitates partnership between both groups. It helps, it helps people know who they've got to talk to. And previously, who were you going to talk to? Well, 5,000 people. A much more difficult conversation. But in the dataset approach, you can just look up the access control lists, see who's part of it, and bingo, you know who to talk to immediately. We unpicked another problem. Appliances limit the impact of bad behaviour, and it becomes an internal problem for the research group to sort out how they see fit. Our standard appliances have pre-committed bandwidth, so if a researcher actually cripples the dataset, then generally what we find is we don't have to do anything because the other researchers within his group whack him over the head with a clipboard, tell him to stop doing it, and our life is a whole lot easier. So, these simple steps started us on the road to context. The quagmire was now able to be split into datasets with permanent and unique names. Roles and responsibilities were being clearly defined. Within the dataset, we developed categories as a tool for data management. Categories are a template which constrain the almost infinitely flexible lot of combinations that you can implement today with today's technologies. So they sort of bring it down into a set of common subsets that make things a whole lot easier, or more manageable, I guess, lower BAU costs. The type of things that you would normalise would be access controls, assurance around the data, how the data is presented on the network, and how the data is protected. So within your data set, when you split it up into categories, these things come out of the box shrink wrapped. You don't need to go individually tampering with configuration files. Think of categories as the POSIX file system's missing ability to send hints to infrastructure. And this unpicks the issue of infinitely flexible configurations. So if we look back on our distributed files, shared file systems, global file systems if you like, users were finding new and unique ways to set up data hierarchies and access controls, and so then as the infrastructure managers come along, everywhere they look, something's done in a new and unique way. And categories simply normalise that. Categories enable mapping of the workflow through to the technology of best fit, communicating the value of the subset of data within the context of the workflow. So what sort of things would you communicate? Well, perhaps the pattern of access, maybe the level of performance, the significance of that subset of data within the user's data set, or longevity. And this whole exercise unpicked yet another monolithic problem. We no longer back up everything. We protect the data in the context of the workflow. And categories kick-started the discussion about workflows. Previously, when we tried to talk to the research groups about their workflow, we found they were quite protective. However, if we don't actually talk about workflows, instead we talk about their data set and what the subsets of data are, then we start breaking, then the researcher inadvertently starts talking about their workflow. And with that knowledge inadvertently handed over, we were able to tune many of the workflows, often getting order of magnitude reductions in their runtime. And we established the relationship between owners, domain specialists, users and consumers. These relationships are authoritatively defined and maintained in access control lists. And when the data set is created, the keys, i.e. the ACLs, are simply handed to the dataset manager. Then as the use of the dataset evolves, the dataset manager can add and remove access as they need. And this forms that valuable bit of metadata information that we have access to when we need to do some sort of infrastructure work specific to that data set. And what we've found over time is these relationships have extended into communities of competence, where existing domain-specific workflows are then remapped to new data sets. Another benefit is because we've containerised things and these communities have started to come into shape, each community can mature its own approach to maintaining the internal structure of data set of the data set and establishing what looks good in terms of their workflow. So there's a lot of flexibility. Even though we're limiting the infinite possibilities, we do this in a way that keeps people focused in the direction they need to be heading. So, as workflows matured, we've seen science applications start to evolve, and these essentially enable domain-specific data sets to be usable by non-domain consumers. So we've got examples of this on our iPhone. Yeah? 10 or 15 years ago, Google Maps was a function of a domain specialist. Right now, you just install it and move on. Right, so that's essentially what a science application looks like. One of the ones internal to CSIRO I'm going to take you through now. But first, let's consider the New South Wales Fire Service. The New South Wales Rural Fire Service is the largest volunteer fire service on the planet, with 75,000 members in 2,032 brigades grouped into 125 districts dispersed over an area of 810,000 kilometres. So these guys are spread across an area that's larger than Texas. So I'm just setting the context for what a science application might look like that's valuable to the community. If you're in that brigade or you're running that organisation, think of the difficulty in training, predicting scenarios and running real-time contingency. Right? Then step back a bit and think about the 2009 bushfires in Victoria, which burned from the 7th of March through till 7th of February to the 4th of March. On 10 major fire fronts, killing 173 people. It wiped out entire towns. 1,800 houses were destroyed in the Kinglake area alone. So, New South Wales Fire Service, training and running operations across an area larger than Texas. What can CSIRO do about that? We have the Pyrotron. The Pyrotron is effectively a contained bushfire. I know the guy that built it. He's hand-engineered many of the instruments himself, and he gathers an enormous amount of reference data out of that. There's another tool we've developed called Workspace, and it's essentially an interactive workflow development tool. And so taking that sensor information and research workflows, combining it with Workspace that allows interactive development, they've developed a tool called Spark. And this is, where I see the magic around workflows happening. This is a tool developed from real research workflows. It's turned into something that can be published. You can put it on your iPhone, and then you can run your own bushfire simulations. So, back to the New South Wales Fire Brigade, they've got a way of demonstrating to people how fires may progress along the countryside. And we've got very diverse terrains. You can program it with all sorts of different wind conditions, and then you can predict or at least see how scenarios may play out. So this is the type of thing that we're seeing in terms of in the science space, science application space. Other leading researchers are doing similar things where they're integrating lots of peer-reviewed workflows. And I guess the way to think about this is previously, if you were to look at the floor tiles on this stage, you're looking very two-dimensionally. But if you can start to stack different domain data sets on those floor tiles, say for instance geotech surveys, native vegetation, hydrology maps, heritage listings, government planning instruments. So you take your floor tile and you stack it with these multi-domain data sets, then suddenly you can come at the problem sideways. Suddenly each floor tile has a personality, and if you're a business or a government or a local council making a decision, suddenly you've got a much better position to be in. And Edward King is one of the scientists who's led the way with this, and he's done a thing around e-reefs, which consumes river hydrology, dredging developments, land use to work out what the water quality is on the reef. So let's have a little bit of a look at how we matured. About 5 years ago, we undertook an extensive review of the data processing and storage issues that our researchers were facing. We established a capability and capacity backlog, which enabled us to see the things that we weren't doing well, the extent of pent-up demand. It enabled us to prioritise within a budget-constrained environment, and importantly, to communicate back to our researchers. We drew a line. Below the line, technology is consumable, replaceable, and a discardable commodity. There are some pet components, but for the most part, it's a herd. And we manage this via a layer of automation and virtualisation. And it is just a layer. It is not layers of virtualisation. This layer serves the purpose of effective deployment and redeployment. And below the line, researchers can get on with defining what looks good for their workflow. The pool is non-blocking, low latency, high bandwidth, and low cost, low footprint. We don't have theoretically perfect networks. For the most part, everything is one hop to anywhere that matters. We're not building monolithic systems like some of the participants here are. Our use case is different. And this is technologies of best fit targeted against the generalised subset of requirements. We're not trying to deliver a perfect solution. We are trying to deliver to the general pool of requirements. Above the line, the generic pool is customised to the specifics of each known good workflow. And as with the dataset boundary, the above the line, below the line principle facilitates partnership between technology specialists and researchers. And this has been a game changer for us because it minimises point solutions. When a workflow exceeds its current allocated capacity, we can assign more. If there's a workflow there that's underusing its capacity, then we can drag it back. So we talk about fit for purpose as if it's a static target, but research is a voyage of discovery. So we need to be able to right-size the infrastructure as workflow requirements change. Today's fit for purpose infrastructure will not be tomorrow's, and that's what it's all about here at MSST. We're looking to the future. And what better way to accelerate the uptake of a new technology than by having the ability to remap a workflow. Remember, the workflow is where all of the effort and the cost goes in. We don't want to have to rewrite it. We simply want to be able to remap it from an old technology to a new technology. What about if this week I hear about a new technology that's going to be applicable at some point in the future to some of the workflows that are being developed? I could actually create a dummy category for that workflow to be sitting on. And sure, it's not sitting on the most optimal hardware, but the workflow is developed, and over a period of time, it'll become cost effective to replace that category of technology without rewriting the workflow. Layers of abstraction enable us to scale up. So what does the crossing the line look like in real terms? So here's a generic workflow, and the layers of abstraction allow us to scale up to the computational facilities of best fit, and we're working hard on being able to do that out into the public cloud and into more of our partner organisations. So in summary, we came for a position where data, code and compute were isolated by our approach to HPC. We engineered a solution where data, code and compute are all now directly connected. With these key ingredients tightly coupled in a dynamic and reproducible and technology agnostic manner, our researchers are able to get on with their job rather than thinking about technology. We have fit-for-purpose storage appliances directly coupled to purpose-built cloud and HPC assets, and we deliver this using a base image that allows floating of the researcher's workflow. They can develop their workflow on their desktop if they like, float it into the research cloud, into HPC, and back again. They can even float it into the storage appliance if really low latency access is required. So now that we've got all of that, now we're seeing science applications turned into high value applications that the community can use. And we've got scientists focusing on the workflow rather than infrastructure. We want to make our high value assets discoverable, assured, and consumable. So, what are the underpinning mechanisms that we would use to make this an automatic outcome? So if you think now around the dataset approach and what the researchers are doing, a lot of stuff is just now automatic for them. They don't need to think about access credentials, they don't need to think about backup protection or any of those things. It all just happens automatically. Now, what would we do to make discovery, assurance, and the ability to consume an automatic outcome? Well, discovery is a function of metadata, and CSIRO has been doing this for years. The limitation is it's generally manual and an afterthought. I guess we've seen a whole lot of research projects that have been forced down the path of comprehensive metadata collection. Assured, trust or assurance means knowing the provenance, and it's the key to reproducible science. It's a fundamental foundation to integrated quality assurance. If you have a buggy program somewhere in your workflow, then you'd want to know where that is and how we can backtrack all of the results that have been derived by that buggy program. And consumable could be a function of the semantic web, amongst other options, of course. So let's look in detail at these three important capabilities. Metadata is a pathway to making data and workflows discoverable. Now, metadata can get particularly confusing and very quickly. I've watched the discussion around metadata now for 5.5 years, and I'm amazed how many different discussions are going on in parallel. So in this particular case, all we are talking about is how the file was created, what created it, what credentials it had at the time of creation, and any metadata that we can grab from the upstream processing. Now, we already know metadata was traditionally used in card catalogues of libraries. Now metadata is used extensively for classifying and discovery of digital assets. Historically, CSIRO's got around 300,000 pieces of code floating around the research environment, and these have been developed without any metadata. So how could I, as a potential consumer, A, find them, B, work out what they're about, C, even work out who the developer was? So metadata is an important thing, and it's not something you can do after the fact. The way to think of this is in terms of a birth certificate. Once the baby has been carried out of the hospital, unless a birth certificate was issued, then that detail is lost. The birth is a fixed point in time, but the metadata requires fixity or the details disappear forever. Provenance. Provenance has been flagged as one of the significant issues facing scientific computing today. Provenance is essentially the chronology of ownership, custody, or the location of a historical object within the Australian Federal Police. We call this the chain of custody, and it is the foundation upon which you build your case. As discussed by the keynote speaker at CSIRO's CSS Conference in 2014, science was facing a credibility crisis, and the figures that Dr. Stodden mentioned were less than 20% of research at that time could be reproduced. Less than 20% of e-research was able to be reproduced. Now, there's a word for the other 80%, right? In fact, there's probably many words, but it isn't science. And, of course, the semantic web. So, what is the semantic web? Who's got iPhones? Androids? Hold them up. Yep. type in news.google.com. That's the web. The semantic web isn't much different. It's pretty easy to understand. The definition is extensive, and I'm not proposing that we would use the semantic web as a way of consuming and processing big data, just that it forms part of our future solution in terms of making that an outcome. So this looks very similar to the story around data code and compute, and I think the challenge is similar. We want to make the experience transparent. We want to make it a given. We know there are plenty of people out in our organisation doing great jobs of metadata, plenty of people doing the hard yards around provenance, plenty of people playing with the semantic web for whatever reason they feel that's appropriate. We're looking at how we can establish a proof of concept around our dataset architecture and link these things into a single unified outcome. It's essentially cradle to the grave metadata, the knowledge about who did what to whom, when and how, with the integrated ability to annotate the why. Remember, the machine can pick the first four, but only the researcher knows what the why actually looks like. And this is essentially context capture. We want to preserve metadata, we want to establish provenance, and we want to present it out immediately through some sort of interface that's readily consumable. So let's just look at how well we used to strip data in the past. One day in the scientific world, in a galaxy not so far away, an instrument recorded some data into files. The instrument was expensive, it was well maintained, well managed, calibrated precisely and operated by a professional, and importantly recorded extensive metadata. In addition to the instrument, someone is funding this data collection. There is external metadata, the project, the budget, the organisation. Now what happens? The researcher, keen to get on with the job, downloads the data, leaving the metadata heading towards the trash. Now, this isn't anyone's fault because we're all very focused. And when I return from this trip, I'm sure there's going to be receipts for transactions that I'm entitled to claim that I've inadvertently lost. And the researchers are driven. They have to get the answers out, so they don't necessarily think about some of the details. So what can we do to help this researcher? So let's start afresh. At the time when the researcher starts, he's got a blank dashboard. The researcher starts by requesting a data set. We don't ask them any technical questions like how big should it be or what are you going to do with it, simply what the project is that's associated with it. Because that project is recorded in a number of different business systems, and we can extract a whole lot of really valuable metadata from them. We can know who's paying for it, what project it is, who's working in there, who's going to be a contributor, a consumer, etc. Maybe even how long the project is going to last. So we can effectively issue a birth certificate for the data set. Moving along, the data set is going to go from 0 bytes of data to ingesting its first file. So in the future, we want to be able to capture not just the file data, but we want to be able to preserve the wealth of metadata information associated with that data. And you've got to do it at that point in time. The instrument, calibration, protocols, versions of code, etc. We want to be able to do this in a manner that's consistent with the births, deaths and marriages register. And it has to be a matter of course. Furthermore, it needs to scale and as it grows, as these births, deaths and marriage entries grow, we need to be able to consume them immediately. I guess this is similar to what we did with respect to backup. Previously, backup was an afterthought. You know, the users would dump all their data and then they'd go and make yet another service desk request to see if it was being backed up. And if this was sensor data, you know, that was going from A to B to C to D, there was no actual, you know, closing of that loop. When could the sensor have its data deleted? Because we knew the backups had happened where the sensor data had been dumped. So we inverted that and we turned it into a process where the data was stored and authoritatively protected all in the one pass. And I think this is going to be key in this approach to presenting this information, that birth certificate needs to be immediately consumable. So CSIRO's got about 4,000 research projects, and listening to the conversation today, I've heard sort of varying views on whether you can normalise the discussion of any given application into a group of generic workflow steps. I guess what we're trying to do is be a safety net. You know, these research projects are ploughing ahead. We're effectively a safety net that just tries to catch everything they're doing, and then we're gradually increasing the scope of that safety net. So if we use a real-world example as an illustration of this, in the bad old days when you wanted to assess a plant's growth, you had to do it destructively. Each week you would cut up more plants, you'd measure the leaf area, weigh the stems, etc., and you'd keep all of those details in handwritten notes. There'd be an audit trail. Obviously that meant you had to grow hundreds of plants and your results were clouded by genetic variation. Now, a few years ago these guys got together and developed PlantScan. This was an amazing tool that was able to spit out petabytes of data in a very short period of time. But essentially it automated all of that process, and they've got a workflow that they've peer reviewed and it's all very good. So my question here is, how would we take PlantScan and add value to that existing workflow? And if we look at a high-level overview of the workflow, there is a plethora of metadata all the way through this process. Right, so what we want to be able to do is, we're already good at storing data. We want to get very good at capturing that data and capturing the metadata and storing that at the exact same time. I hear people saying object stores solve that problem. Is that what I hear? Jake, are you saying that? So say we can do this. I mean, this is all theoretical and we're exploring it in the form of a proof of concept, but if we were to do this, what were the benefits going to be? One is repeatable analysis. If we can automate this, it becomes a tool in the researcher's toolbox. You know, researchers are really struggling to achieve results, and I don't know if you noticed, but, you know, climate scientists seem to take a real flogging whenever they release some new sort of finding that we're all going to die. I mean, and so this would act as a safety net that's preserved all the detail and allow them to, you know, just go back and double check, give themselves their assurance around what they've done. It also would facilitate peer review. If you've got the exact process that you followed through, then peer review becomes faster as well. The second benefit I'd see is quality assurance. So back to PlantScan, if we notice the camera was knocked out of alignment somewhere between calibration run 13 and 14, then we can simply identify all of the potential bad result files and eliminate them. Maybe they want to do some offset processing or something, they could do that if they wanted. But essentially it becomes a much easier step, and it's integrated. Okay, and similar, if there was a buggy version of the assay software that was unable to properly analyse wheat leaves or whatever, then potentially you could fix that bug, replace. And remember, we've been doing this in the IT industry for a long time. It's called make. Yeah. You touch a bit of source file and you run make and it just does it automatically. So we're not talking about something that's too far over the horizon. Benefit 3 is immediate consumption. I know I've sort of said many times throughout this about putting this data out through some sort of semantic web interface so it's immediately consumable. To me, it is a metadata function, not unlike a file system. It's got to happen synchronously. And the key benefit there is we've got a lot of projects that are codependent on each other. And at the moment, the handover of data is manual, right? So just like the backup is an afterthought and we fix that, this actually goes to the heart of streaming data through our different research projects where interdependencies exist. And then finally, I think we've heard this before, benchmarks and tuning. Any published workflow now becomes a potential as a benchmark. Finally, infrastructure management. There's metadata, obviously, in the POSIX file system. It's next to useless for doing a lot of the infrastructure management that we need to be able to do today. It was great 10 or 20 years ago. It is not that good anymore. We need to be able to see more context. We need to see how often a file was accessed, what areas of your tape-based file systems, you want to know the segments that were accessed, that sort of thing. Who was consuming them and how the data was performing. Remember, we're in a very budget-constrained environment. Every petabyte of data that we over-provision or over-protect is another petabyte of research data that we cannot store or process. So optimization is high on our list of priorities. And then finally, as the number of research workflows proliferate, one of the things we can't do at all at the moment is discover past failures. Now, if you're a researcher and you want to get a successful outcome to your research, wouldn't it be good to look up the past 173 failed attempts to do that? Right, so if we can drag this along for the ride, discovery of failure becomes a key tool to optimising the pathway to success. And with more and more organisations competing to be first improving or discovering things, it'd be good to, get up to the pole position, if you like, on the raceway. So let's look at this in the context of an example from the past. In Unix, everything is a file, pretty much. There's a well-written set of simple tools that we can tie together in a pipeline. It looks like a workflow. It doesn't necessarily require programming, and it turns out a higher value output in a reasonably robust manner. Now, in the future, my thoughts around this is everything is a data set. Those data sets are domain specific. Mere mortals can't understand them, but we've got researchers who've taken their intellectual property, turned it into a workflow, and then suddenly we've got a science application that is potentially consumable if the interfaces are all compatible. So wouldn't it be good if we could get our science workflows, our science applications, to be that set of pluggable tools where we could start to link these workflows in ad hoc and unique ways to answer the questions that we will face in the future. Yeah. I think there's a whole lot of additional value in science workflows that we can extract over time. So just recapping briefly, over the last 5 years, we spent a whole lot of time and effort getting the infrastructure to a place where researchers could focus on combining domain-specific work data sets with their own intellectual knowledge and creating workflows. This is just happening. It's a great thing to watch. We can now see the possibility of compound workflows such as those in the Spark application deliver high-value propositions to organisations like the New South Wales Rural Bushfire Service. Things that just weren't possible to describe to people can now be shown to them on their iPhone in terms of a simulation. If we think of workflows as books, each one with a new and unique piece of knowledge, then as the number of books in your library grows from 10 to 100 to 1,000, maybe 10,000 in your library, you rapidly gain an appreciation for the Dewey Decimal Classification System, i.e. you get to the point where you either store things according to Dewey Decimal System or you just lose information, right? And given science workflows are potentially so valuable to us, do we really want to lose them? So, as we move from where we are today into the future, we want to get to a point where our workflows are discoverable, assured, and just like the books in your library, they can be consumed. Cool. So that pretty much ties it all up for me. Questions? Thoughts? I'm particularly tired, so if there's anything I sort of skipped over or drilled through, feel free to criticise or tell me I'm smoking dope, whatever.
I got a quick one for you. I'm working in a similar space, and the difficulty we run into is the human factor of extracting the workflow from the researcher. So what kind of people do you need to figure out what this workflow is and then turn around and automate it? Like, what kind of skills, and are these dedicated roles?
Yeah, so that's a really good question. So the key we found was talking to them about their data set and splitting their data set up into subsets. This took down the defensive barrier of we're not going to tell you our intellectual property, right? So that was part of it, but you definitely need someone with a breadth and depth of skill. If you just send a traditional IT business analyst into that role, then you're going to get bad results. So I'd say it's not straightforward. What discipline or domains are you working across?
We're working across domains. So we're building a commercial application that does something similar to what you've built as your internal set of tools. Right. And all of our clients start talking about metadata and workflow, and then they start scratching their head and they say, could we just back up our data and shove it in a tape archive? Yeah,
so right. So there's a lot to that. There's a lot to that answer that question. One is it's going to take generational change. Right? In our organisation, 5,500 people, or 5,300 at the moment, there are researchers that will retire before they change their habits. Right? Then there are projects that are midstream. Right? Now, if you try and step into a project midstream and change them, you're going to end up with a lot of angry people on your doorstep. And then there's projects at the point of initiation. So they're the low-hanging fruit. Right? And you've got to allow them to make mistakes.
So one last question then, which is, do you need to change or define the way the researcher works, or are you able to dovetail with whatever nonsense they seem to like to do?
So the way I treat that problem is that they are very cooperative when I can make their workflow run 10 times faster. So that's always been my focus. As I'm sitting there listening to them articulate, I start from where are your pain points, right? And generally we can find things that get them on board through a carrot type approach rather than forcing them to redefine. So I don't see, to answer your question sort of more holistically and more broadly for the audience, this is a very long play, right? We've got, some of our researchers have got 45 years of doing things their way. They're going to keep doing that. Others who can see the benefit get on board, and then you've got groups of people that are actually forward-thinking.
So a question for you. How, I could see this applying to just, enterprise IT kind of problems. For example, we have, I think, Randy Olinger from United Health Group is here. They're like, health companies are often interested in a 360-degree view of the patient. So there you've got records of treatment, you have billing records, you have all sorts of data streams, digital exhaust from the devices maybe they carry or wear. This seems like the same kind of problem? Couldn't you apply the framework to that kind of problem as well?
Yeah, so I guess in the proof of concept that we're designing at the moment, that'll be the plan. So if we look at the Murray-Darling Sustainable Yields Project, they've done a whole lot around metadata, and then there's some other groups of people that have been tied up in that whole semantic thing. They've done the Murray-Darling Sustainable Yields did a whole lot around provenance because they feared they were going to get their asses sued, right? So they were really, really careful to keep very precise records, but it's all bespoke. So we think we can take that. We know the metadata thing is a nightmare, right? So we've got to sort of approach that from a layered standpoint and plugins, right? So there's, if we can do it so that the basic metadata that we collect or, that augments the data set, if we can do that in a way that you can then have a plugin that knows how to reach into a specific instrument, then I see that as a pathway to extending it once we prove it as a concept, right? And then was there another part of that question, or did that sort of almost...
Well, there's another, so maybe an unrelated, but it's another question I had was just, so if your model is like Unix, kind of the Unix, commands
pipeline,
and pipes and stuff, what's like, or can you give us like an example of like a use case where a pipes sort of concept would apply?
So we're already seeing that. So with the research vessel, with the investigator, we have a provenance chain from the instruments all the way through to the long-term storage facility, and part of that provenance chain is piping of XML. You're effectively piping XML from process to process to process. Okay. You know, so that's where I'm sort of taking the example. I'm not saying that I fully understand it, and I don't think, I mean, it could be 5 or 10 years before we fully understand this. But at the end of the day, the Unix pipe was essentially new line delimited ASCII characters. This is just a more complicated or more structured approach, and we've just got to approach it in layers. So that as it goes, you know, you want to be able to filter out things you don't want. You want to be able to make assessments of things, you know, around calibrations and the like, that sort of thing. Yeah.
John?
So you mentioned your repository of plants, insects, maybe animal specimens.
Yeah.
Are you doing any DNA sequencing there? And does that
Yeah, we'd be doing DNA sequencing. So there's a whole lot of stuff on the web that you can read. I'm not in direct contact with those guys. I know there's a lot of sequencing that goes on. My understanding is they're basically following both tracks, sequencing and actual growth characteristics, and then trying to align the two. That'd be about the extent of my specific knowledge in there.
Okay.
But if you go, the link that was back there actually goes into a fair bit of detail. You can drill down, I think, that link there, I think, you can drill down in there and they start to talk about all of that stuff.
Okay. And how do you see the evolution of, as the technology increases, whether it's DNA sequencing, three-dimensional imaging, other new technologies that come on board, increasing the size of your repositories? How do you see that impacting your facility, plus the need to perhaps more migrate from one format data representation to another?
Yeah, so that's really good. I like that. So we're already facing that challenge. We have a tool called Logical Collection Manager, and the reason that was written was to capture this vast swathe of unstructured data and put containers, boundaries around it to make it sensible. And then we store that within categories as well. So one of those categories is the ATNF Pulsar archive. It's about 250 terabytes of data, and we see the need to be able to store that along indices of access. Is that getting towards an answer that you're looking for? Okay, so essentially the way the data is stored is the way that it is collected, but when they access it orthogonally.
Okay.
Right, and so when we store it authoritatively and protected. Right, I see there will be an indexing function, right, so that when it comes time to process it, it comes back along the indice that you want to access it along, right? Yeah. So in the whole gene sequence thing, I'm not as familiar with that area, but I can imagine that there are similar problems. I don't know what the answer to those look like. I've got a rough idea what the answer to the pulsar problem looks like. Yeah. Does that address your question?
Thanks.
Yep, cool.
Can you describe a little bit how you're searching all of this metadata, and whether you're doing any access control of the search itself? Like, are there certain data sets that certain researchers don't have access to or do have access to, and how any access control is done across a search?
So today this is our metadata search engine. And it's around published data. I guess the example I gave at the end is around a proof of concept that covers the breadth of working data. So at the moment we don't know what that looks like, but it will definitely have access controls around what you can and can't pull back. My background's from high security environments, and so I wouldn't be surprised if they don't look like achieving those security principles. But within this portal at the moment, data can be my goodness, the word escapes. I mean, not quarantined. There's a embargoed. Yeah, so you can embargo your data set. You can publish it in here and embargo it, and only the people that are entitled to use it during the embargo period can actually see it or download it. then there's a whole lot of licensing structures that are involved in that so that you can restrict on that. It's not particularly fine-grained. I don't think that, for the most part, the research community is going to be served well by fine-grained, and I don't think that that's necessarily served the secure facilities particularly well either. But yeah, in the future there will be more, and that will be part of that proof of concept we're trying to get to.